pleasure to have Barry Nelson joining us, who can give a talk today. So Barry is the professor at Northwestern University. He's the Walter Murphy Professor in the Department of Industrial Engineering and Management Science. He's also a distinguished visiting scholar at Lancaster University. His background is in industrial engineering. So that's what he did his PhD in at Purdue University, and then before that, an undergraduate in mathematics and computer science. I'm not sure if Barry would agree with me, but I would call Barry an operational researcher. So I think a lot of Barry's research appears quite prominently in the operational research literature, but then also touches on many other interesting areas like statistics and machine learning. So his primary focus has been around computer simulations, stochastic processes, statistical learning, particularly looking at the statistical aspects of computer simulation around input uncertainty and dealing with sort of statistical considerations there, but also in areas like machine learning, such as Bayesian optimization, and how they fit into computer simulations. Okay, so I'll pass over to Barry, who's going to give us a wonderful talk. And please, at any point, add questions to the chat, and I'll ask them to Barry at the end. Go ahead.
Thanks very much, Chris. It's an honor to be asked to speak in this, and I've enjoyed watching some of the past talks. And one of the things I've learned while being associated with Lancaster is how to switch between operational research and operations research, depending upon what country I am in. So Americans would typically say operations research. So computer simulation may be the most ambiguous term in our field because it can mean so many different things. So what I wanted to start with was just to say, what does computer simulation mean in operational research? And for that, I'm going to pop over to some simulation software. And assuming that this is not too small for you to see, this is a simulation model of an airport check-in and security system. And an operational researcher would build such a model in order to improve the performance. For example, we might want to allocate our budget among kiosks and check-in and security facilities in order to get people through security as fast as possible in order to get to their gate. And a key thing about the kinds of simulations that I deal with is that they are inherently stochastic. So there is uncertainty. The arrivals and passengers, who forgets to remove the bottle of water from their luggage. And so when we talk about improving or optimizing this system, we're going to be optimizing some performance measure. For example, like the expected make span, the time to get, say, 2,000 people through security. All right. Oops, let me stop this simulation here. All right, Chris, you're seeing the slides again, right?
Yeah, that's fine.
Okay, good. So I think of simulation as data analytics for systems that don't yet exist. Because what we're going to do is we're going to create data and use that data specifically for system improvement. Now, this type of simulation is used for all kinds of applications, and I've listed 5 here that I've been involved with, either as in research or in consulting. So staffing call centers to cost effectively keep low hold times for callers. Optimizing protocols for dispatching and treatment of stroke patients so that they get the right treatment at the right facility as quickly as possible. Designing multi-billion-dollar semiconductor wafer fabrication facilities to get low manufacturing cycle times. Interesting recent project on right-sizing air vertiports for proposed air taxi systems in a major city. And a classical sort of industrial engineering application, optimizing reorder policies and delivery services for an online retailer to try to achieve same-day delivery. And what's fundamental, again, to all of these systems is that we're trying to optimize or improve performance in the presence of natural variability, right? The system is inherently stochastic, and we have to somehow account for that in our simulation model. Now, how do people do this? Simulations are often done in programming languages like Python. These they provide libraries of class libraries and functions that are needed to support simulation. They typically take a discrete event worldview, which means that you describe what happens at each event time in the simulation, and SimPy is an example for that. But there are lots of commercial simulation languages. It's actually quite a thriving market. Simio, which is what you just saw, Arena, Simulate, which is kind of the dominant product in the UK, AnyLogic are just some of the standard ones out there. They typically take a process flow worldview, which is describing the flow of, say, people through the airports. As you saw, nice graphical user interfaces for modeling and animation, and they often try to integrate the statistical analysis capabilities within the simulation language itself. Today, what I want to talk about is what we call simulation optimization. And I'm going to give a very generic description here and then bring it down to the topic of the talk today. So it's an optimization problem. We're going to maximize over some decision variables x, a function that I've called mu of x. Now, mu of x is a summary measure of some random output of the simulation. So I called that y of x, and here we're looking at the average of the expected value. So in the airport example, the make span to get 2,000 people through security, that is the amount of time it takes me to clear security, trying to minimize the average time to do that might be a typical simulation optimization objective. The decision variables x in the current example could be the number of check-in kiosks I have versus the number of real people check-ins, the number of security lanes I have open, things like that. And they'll be subject to some constraints, some of which are deterministic, for example, a budget constraint, and some might be stochastic, meaning that they are other performance measures in the simulation, such as the links to the queues at security, and I'd like my solution to somehow manage those other stochastic elements as well. For example, I might like the expected length of the queues to stay within some sorts of boundaries. Now, just like mathematical optimization, linear programming, integer programming, nonlinear programming, the nature of the feasible solution X, finite, countable, uncountable, has a big effect in simulation optimization of how we go about attacking the problem. And for those of you with backgrounds in math programming, you might have looked at my formulation and say, well, that looks like a stochastic program. That looks like something I've seen in a mathematical programming class. The key difference in simulation optimization is those expected values, I have no way to evaluate them, but I can simulate them. That is, I can generate realizations of the time to clear security and the queue lengths, and thereby estimate those and try to optimize or satisfy constraints. And usually in simulation, we don't assume we know a lot of structural information about these random variables. Now, anytime I give a talk on this, I always like to start by depressing the audience by talking about what can go wrong. So what are the three sources of error that can occur in simulation optimization? So for notation in the talk, I'm going to use X star to be the optimal solution, the best setting of those decision variables I can have. I'll put a hat over it to indicate what my simulation optimization algorithm gives me at the end. I'll let mu hat of that solution be my estimate of the objective function value, for example, the mean time to clear security. And no matter what sort of simulation optimization algorithm I run, it's going to visit some sequence of solutions. So I'm going to call those X1 through XK. That's whatever solutions I actually simulate during the course of the algorithm. Okay, so what can go wrong? Well, the first thing is I might never simulate the optimal solution, right? Particularly if there are uncountably many solutions, I'm almost certain not to do that. So in general, nonlinear optimization, this is the same sort of error that we face in math programming as well as simulation optimization. But the second one is different. I may not even recognize the best solution that I actually simulated. So imagine that at the end of my simulation optimization run, I'm going to pick the solution with the best objective function value, say maximum value in a maximization problem. Because I only have estimates from running simulations of those objective function values, that may not actually be the best solution I simulated. And finally, a more subtle error is When I do that, I'm picking the largest of a bunch of random variables, which means that I'm going to, in general, have a biased estimate of how good that solution actually is. So I didn't see the optimal solution, that's number one. I didn't recognize the best solution that I actually simulated, that's number two. And the solution I picked to implement, I actually have an optimistic idea of how well it's going to work. So this is where research and simulation optimization comes in, is in dealing with these sources of error. And I'll talk a little bit about those as I go along. So in this talk, I'm going to focus on X's, decision variables, that are either integer ordered, like the number of kiosks that I decide to put in my airport check-in, or possibly categorical, but only a finite number of them. Now, my optimization colleagues would say, well, finite number of solutions, that doesn't sound like a hard problem, but remember that I've got to run potentially computationally expensive simulations at any solution that I want to evaluate. So a finite number of solutions is still a problem for me, particularly when it's large. So I'm going to talk about situations where the number of feasible solutions are large, where I mean on the order of, say, millions of feasible solutions. And I'm going to talk about two different approaches to this kind of problem, depending upon a characteristic of problem. So the airport check-in problem I showed you fits in the first category. Each replication of the simulation, right? So pick a setting of number of kiosks, number of security people, and simulate it. You'll typically do multiple replications because you want to get a good estimate. The replications themselves are relatively cheap, but significantly noisy. And the approach that I'm going to take is to use overwhelming force on this problem, and I'll indicate next what I mean by that. Then I'm going to finish by talking about problems where every replication is very computationally expensive, but the noise is more modest. Probably the worst case I ever had on this was simulating a fuel injector manufacturing company, and it took us 8 hours to get 20 replications of a single solution. So it was incredibly slow and incredibly difficult to run. And the approach in that case is going to be to decide very carefully what I simulate next. So make a very, very careful decision, because each solution I choose to simulate, each feasible solution, is very expensive to do. All right, so that's the outline for the talk. First, overwhelming force. Second, be very careful. So if we simulate all feasible solutions, then I can control all three sources of error, right? I will definitely have simulated the optimal solution. And if I control the amount of simulation effort that I spend on those solutions appropriately, I can also deal with the selection and the bias error as well. Now, that's a pretty simple optimization algorithm, right? Simulate everything. But it can be trickier than that. So I got a little bit ahead of myself. The first thing I wanted to say is cheap parallel computing greatly extends the exhaustively simulate them all limit. So I just took a look yesterday to make sure I was up to date. And on Amazon Web Services, I can rent a very high-end CPU with multiple threads for 22 cents an hour, right? So high performance parallel computing is extremely cheap. And that allows me to extend the kinds of problems where I can potentially simulate them all. Now, what the talk is going to deal with today is that parallel simulation introduces both new statistical problems and new coordination problems that we hadn't had to deal with before. And in particular, in parallel, being efficient is not just being statistically efficient. Up until recently, when we thought about an efficient simulation optimization algorithm, we meant minimizing the number of times you have to run the simulation, the number of replications you have to get, statistical efficiency. Now, computational efficiency comes in, and that's one of the things that I'll talk about today. Now, I know this may be troubling because I've seen it before. People say, well, wait, X is a decision variable. It's got some kind of spatial structure. You're not going to exploit it. You're just going to simulate every single solution. But from a practitioner's point of view, if what I tell them to do is cheap and it's fast and it controls all those sources of error, then why not do it? right? In the second part of the talk, I'm going to talk about exploiting spatial structure, but that's only really necessary when the simulations are tremendously expensive to do. If we can simulate them all, then we actually can really solve a simulation optimization problem. Now, the approach that I'm going to talk about is in a class of approaches called ranking and selection. Some of you may have heard of this before. Ranking and selection is a collection of sequential statistical methods originally created in the 1950s for biostatistics kind of problems. I think it's fair to say it didn't have a tremendous impact there, but in the early 1980s, we simulation people grabbed onto this idea, and it's really reached its zenith there, by which I mean practitioners really use these approaches and they're built into commercial software products, and it's really had a big impact in the field. So what does ranking and selection try to do? Ranking and selection tries to sequentially allocate effort, in our case, simulation replications, to provide some sort of statistical guarantee of goodness of the optimization at the end. And I've listed at the bottom the 4 most common types of guarantees that people think about: good selection, correct selection, a solution in the top M, or a smaller subset of solutions that's guaranteed to contain the best or some good ones. So let me focus on correct selection and good selection because they're the most related to the talk today. So correct selection is just what it sounds like. I'd like a high probability that the solution that I select as optimal actually is system K. I forgot to mention up here that I'm just going to number things so that system K is the best, or any solution tied with system K has the maximum objective function value. Now, typically, we can't guarantee that in finite time, so often a compromise is made to say, I'd like a probability of 1 minus alpha of selecting the optimal or best system, provided the gap between the best and the second best is at least some value delta that I get to specify. Related to that is a good selection guarantee, which says I'd like a high probability that the solution I select, that its objective function value is no more than delta, an optimality gap from the best. And these two are by far the most common objectives that people in the ranking and selection world think about. So since I didn't do that as smoothly as I would like, let me just say this again. Ranking and selection treats the K systems as being categorical. It doesn't use any spatial information. I've arbitrarily ordered them so that mu K, system K, is the best, or any that was tied with that. And I'd like to sequentially allocate replications to my simulated systems, so I either guarantee a probability of correct selection or a probability of good selection when the procedure finally terminates. Now, probably half of you out there are saying, wow, this sounds an awful lot like multi-arm bandit stuff. And there definitely is a relationship, but ranking and selection is different and is much more effective in the environment that I'm talking about. If you want to ask me about bandit stuff at the end, I'm more than happy to compare and contrast that. I will say right up front that multi-arm bandit is a much sexier name than ranking and selection. They're explaining why it's so much more well-known. Okay, so these procedures have been around since the 50s. They've been extended by simulation people since the 80s. So what's the research that's left to do? Well, we start to run into roadblocks when we want to talk about really large numbers of feasible solutions, like in the order of 1 million. So the first thing is that probability of correct or good selection are family-wise statistical statements. That means they suffer the curse of multiplicity, which means they're more and more demanding in terms of the amount of simulated data I have to generate, the larger the number of alternatives that I want to compare. And so the first thing we're going to ask ourselves is, does it really make sense to insist on, say, finding the single best system when I have on the order of millions? And I'm going to answer that question in a little bit. The second issue is we have been focused pretty obsessively on being statistically efficient, which means trying to minimize the number of simulations that I have to run. But a lot of the things that we do to be statistically or observation efficient are real computational bottlenecks when we start to do things in parallel. So let me give you an idea of what I mean. A lot of ranking and selection procedures are based on doing pairwise comparisons. That is, I compare solution X with solution X prime and maybe take a running sum of their replications. This is done because the way we simulate systems, we can often induce a strong positive correlation between the outputs at different feasible solutions, which really reduces the variance of the difference. The problem is that K-choose-2 comparisons becomes overwhelming from a computational point of view when K is on the order of millions. Now I'm just waiting to do all the comparisons as opposed to doing any simulation. Now, one of the ways that we use those pairwise comparisons is that we often use them to eliminate systems. So I might look at the pairwise difference between solution X and solution X prime, and if it falls below some boundary here that I've called G, then I'll eliminate system X and keep system X prime, because I'm convinced that system X is so far inferior that I can get rid of it with statistical confidence. The problem is that function G is very much a function of the number of systems I'm comparing. And it becomes more and more conservative, meaning it gets harder and harder to eliminate systems as I'm simulating the more systems that I'm comparing. Okay, so let's go a different route. Maybe we should select very carefully which solution I simulate next, one at a time. I'll do this one, I'll see what I get, then I'll do this one. Well, that defeats the whole idea of going parallel, right? Picking solutions one at a time to simulate is as anti-parallel as I can be, and so now I'm not exploiting high-performance parallel computing. And finally, to ensure statistical properties, at least until recently, my algorithms assumed that I was always simulating the same number of replications from each solution that was still in play, and so that's a lot of synchronization. So kind of the bottom line from this slide is that statistical or observation efficiency comes with lots of coupled computational operations, which therefore defeat a lot of the purpose of trying to do things in parallel. So a few years ago, Susan Hunter, who's a professor at Purdue, and I were asked to think about parallel ranking and selection and to sort of set a research agenda for this. And we decided to not think of it initially as a statistical problem and instead think of it as a computational problem. Okay, so what is a ranking and selection procedure computationally? It's a collection of jobs, right? So later I'm going to talk about a master worker environment where a master will decide what jobs need to be run, and then worker processors will run those jobs and report results. So what would be in a job? Well, a job could contain one of two things or both. It could contain simulation jobs. So in our notation here, script Q is the set of systems I want the processor to simulate. Delta is the number of replications I want the processor to get. And U is the block of random numbers I want to assign to that calculation, which does matter in computer simulation. So that's what we call a simulation job. A job might also consist of calculations. So we use C to say these are non-simulation calculations or operations that need to be performed, like doing pairwise comparisons and comparing them with a boundary, for example. That's an example of a non-simulation calculation. And PJ, and this is the critical part, that's the list of other jobs that have to be done before I can do these calculations. And that's where the computational bottleneck occurs, right? Is that to assure statistical validity of my algorithm, I need to make sure that up until recently, I need to make sure that certain jobs are complete before I can actually go ahead and do those calculations. And that's where I can waste a lot of processor time, idle a lot of workers, and not really get the benefit out of the parallel computing. So as soon as you start to think of a ranking and selection procedure in terms of the kind of jobs it creates, it leads you to create different kinds of procedures. And I want to talk to you about one approach today. So some of our work we call parallel adaptive survivor selection. And it's based on three key ideas that come out of thinking about ranking and selection procedures as jobs. The first idea, not all that profound on its own, says, I'm going to define good solutions as any solutions that are better than some standard. I'm going to call that standard mu star. Now, there are lots of ways you could define the standard. The standard could be the value of the best system. That's the one I've highlighted in blue. It could be a value that's delta below the best system. That's kind of like a good selection guarantee. It could be the nth best value. Anyone that's better than the nth best is considered good. Or it could be, I've got a known constant, like 2,000 passengers per hour. And any configuration that gets through 2,000 passengers per hour is a good one. But if none of them do that, then I'd at least like the best one that we have. So that's idea number one, is to think about trying to achieve a standard. Where it becomes useful is when we combine it with idea number two. So I'm going to change my objective to controlling the expected false elimination rate. So a false elimination means throwing out or eliminating a feasible solution that's as good or better than the standard. This is much more consistent with modern ideas of large-scale statistical inference, where we try to control some sort of an error rate or false discovery rate, as opposed to trying to control this overall family-wise error. And then idea number three is, well, if I knew what the standard was, life would be good. Of course, I don't know any of those three standards that I've listed up there before I start the problem. But what I'm going to do is I'm going to compare each feasible solution's performance individually, not pairwise, to an estimated standard that is learned collectively by all of the systems as I simulate that. Now, that may be a little bit hard to envision, so I'm going to give you one specific example on the next slide that's been very effective for us. So what we call bypass or bisection pass is one specific algorithm that takes this approach. And I'm going to look at the version of bypass where the standard is the value of the best system or any that are tied to it. You can use any of those other standards with it, but this is the easiest one to talk about. So computationally, what's going to happen is the master is going to be sending feasible solutions out to workers and asking them to do a batch of simulations. When those simulations come back, the master is going to do something with them. So all simulation jobs are going to be done by workers. All calculation jobs are going to be done by the master. So what's the master going to do when it gets observations back on a feasible solution? The master is going to compare the running sum of replications, say from solution X, to an estimated value of the standard, which I've called mu bar. And if it turns out that that falls below a boundary, my minus G, then I'm going to eliminate that system. It's gone. Now, what's really critical here is what is the standard, or what is the estimated standard? So the estimated standard is the average estimated value of all currently active solutions, solutions that haven't been eliminated. Okay, so think about this in a minute. In the beginning, the master is going to get all of the feasible solutions simulated. It's going to compute the average performance across all of those solutions. And mu bar is going to be kind of in the middle of all the objective function values. And if they're far enough below, they're going to get thrown out. When I eliminate solutions, mu bar moves up, right? I'm averaging better and better solutions as I go along. So it acts a little bit like a bisection search. The comparisons are only with the estimated standard. There's no k-choose 2. There are only the number of comparisons as the number of systems that I still have surviving. And finally, because I'm doing an error rate, the function G I compare to doesn't depend on the number of systems I'm comparing, right? Because it is a marginal statement. Is this solution better than the standard? Now, the statistical question, and what got my student Lynn to pay her dissertations, is proving that we can actually guarantee an expected false elimination rate less than or equal to some alpha that we specify. That's the statistical question. But you can see from a computational point of view why this is just so much faster to do. Okay, let me just give you two quick sets of results here to give you some intuition. This is actually a really old figure, but I like it because it demonstrates some intuition. So this is an inventory problem, sort of a classical operational research problem. There are 22,500 feasible solutions, which we now consider a really small problem, but when we first started, that was a big problem. I've got 101 processors, one master, 100 worker processors. I'm going to use an expected false elimination rate of 2%. Now, what the blue line shows you is as I spend more and more computer time, how many systems are surviving. That is, how fast is bypass eliminating systems, getting it down to those that are as good or better than the standard. The dotted line says, how well could I do this if I actually started with knowledge of the standard? Instead of having to statistically learn the standard as I went along, that is the value of the best, I knew it from the beginning, I just didn't know which systems met it. And that's the dotted line. So there are two things I want you to see from the figure. One is estimating the standard in this way. We don't do that much worse than if we had actually known it in advance. It pretty much parallels it, except for the fact that we need to simulate all solutions a little bit at the beginning. But the other thing I want you to notice is that bypass is really good in this stage, which is getting rid of lots of systems quickly, and it's not so good at the end game, right? So when you get 4 or 5 or 7 solutions left, it's really not very effective at getting it down to 1, and you really would want to switch to something else. Okay, this second one is just showing off. This is just fresh off the presses here. So this is an Fda research problem, an actual problem that came out of the paper there at the right. There are almost 1.2 million feasible solutions, and they arise by choosing what activities in this project I want to speed up by adding resources. This actually has no spatial structure. It's a totally combinatorial problem. In our latest version of bypass, running it until just one feasible solution survives on just 21 parallel processors took 12 minutes, right? At 12 minutes, there really is no reason to use a more sophisticated algorithm because here we have an algorithm where all feasible solutions have been simulated and we provide a statistical guarantee at the end, which is this expected false elimination rate. Okay, so that's the first idea. If the problem is such that you can afford to simulate all feasible solutions, at least a little bit, then we have computationally effective methods that provide statistical guarantees and, if done right, exploit high performance, parallel, and now very cheap computing. So for the last part of the talk, I'd like to say a little bit about the other kind of problem where the number of solutions may be quite large, but they're incredibly expensive to simulate. So simulating them all is not even a remote possibility. Maybe I can simulate 10% of the feasible solutions or something like that. Now, this sort of computationally expensive setting is where Bayesian optimization really shines. And since I'm not really sure of the background entirely of the audience, I thought I'd just say a little bit about Bayesian optimization magic in case you've never sort of seen this argument before. So in general, there's some function f of x I'd like to optimize, but I don't really know the function. Give me an x, I can return a value, say from a computer experiment. So the Bayesian optimization approach says, I'm going to pretend like this function x is sampled from a space of random functions that exhibit spatial correlation. And then every time I evaluate a solution, say x sub I, I'm going to update my conditional distribution of that random function given the values that I've simulated. And based on that conditional distribution, I'll make a really smart decision about the next solution at which I want to look using some sort of an expected improvement idea. Now, expected improvement is both a specific method and a general idea, and I'll say something specific in a minute. Now, Gaussian processes are extremely popular for the choice of random function because the conditional distribution of a Gaussian process is still a Gaussian process, and that really helps, computationally and technically. Okay, so we want to exploit Bayesian optimization in a problem where the x's are integer ordered decision variables, discrete value. And the first thing you find out if you try to adapt standard Bayesian optimization methodology to this problem is the covariance functions for continuous valued x just don't work very well for integer ordered x. They tend to be way too optimistic. They assume the surface is way too smooth. In general, Bayesian optimization can involve having to invert large, dense, ill-conditioned covariance matrices, and we're wanting to deal with problems with large numbers of feasible solutions, so that's going to come in. And finally, our simulation output is stochastic, and variance is heterogeneous, so some little adjustment like a nugget effect, which is often done, really doesn't capture what's going on in our simulations. So the question is, how can I adapt Bayesian optimization to our environment? So here's a high-level summary of our approach. First is we're going to use a different kind of Gaussian process than is typically used in Bayesian optimization, a Gauss-Markov random field, a discrete Gauss-Markov random field. And we're going to enforce a spatial structure that makes sense for integer problems. And I'm going to show you that in just a second. The nice thing about a GMRF is it's defined in terms of its precision matrix, which is the inverse of the variance covariance matrix, which we're going to create in such a way that it will be sparse. And this has tremendous computational payoffs as we go along. We're going to take the idea of expected improvement, but extend it to our setting, which is stochastic. So we call that complete expected improvement because it really accounts for the full level of stochasticity in our problem. What we show is that CEI is more effective than standard expected improvement acquisition functions in this. And again, from a computational point of view, a nice thing about CEI is we never need the full inverse of Q. To compute CEI, and I'm going to show you more about this in a minute, we only need the diagonal and one column of the inverse, and those are things we can actually get without ever having to do a full inverse. And finally, in our optimization algorithm, we're going to alternate between global search using the full posterior distribution across all feasible solutions and what we call rapid search, which is taking a promising subset of solutions and exploring them very intensely. Now, this is a kind of a standard approach in many optimization algorithms, but the nice thing about working with a GMRF is any subset of a GMRF is also a Gauss-Markov random field, which means our rapid search promising subset do not have to be close in space. We can pick solutions all over the feasible region that we believe have promise and then explore those without having them to be spatially close. Okay, I want to be sure to allow time for questions, but I think we're on track to do that okay. So this is the one really technical slide in the talk, and I wanted to give you a little bit of an idea of what a GMRF is. So let's start with the picture. So a GMRF has nodes and arcs. So in our context, a node is going to correspond to a feasible solution. So I'm going to take a really simple two-dimensional problem, x1, x2, where x1 is the reorder point for iPhones. When your store gets down to x1, you're going to place a new order, and x2 is how many you're going to order. And you'd like to decide what x1 and x2 should be to maximize your expected profit over the year or something like that. So you can see on the right in the picture, each one of those nodes corresponds to an x1 or x2 solution. Now we're going to define a neighborhood around that by putting in arcs. The arcs, the neighborhood structure that's worked really well for us is the one shown here, where any solution, feasible solution that differs by one in one coordinate direction is a neighbor. So you can see that we've put arcs in there. So for example, for solution 1, 3, its neighbors are 0, 3, 1, 4, 2, 3, and 1, 2. We're going to define the GMRF by this graph. Now, what that means is the only non-zero elements in the precision matrix will be where there are arcs, which is going to, as I'll say in a minute, make a precision matrix which is very, very, very sparse. Now, why is this even a reasonable thing to do, right? Are we just making it up as we go along? Well, the Markov aspect of a GMRF is as follows. So if you look at solution 1, 3, which remember, I'm treating this as a sample from a random function, the Markov property says that if I have simulated all of the neighbors of solution 1-3, but haven't simulated it, there is no additional information in the space about 1-3 beyond what I know there. So it is conditionally independent of all the other feasible solutions, given that I've simulated its neighbors. This turns out to make a lot of sense for integer optimization problems. The kind of response surfaces we deal with are very well characterized by that structure. There's not a lot of long-range dependence in them. If you know the neighbors, you know pretty much everything there is to know. So as opposed to what's often done in statistics, trying to infer where the arcs are in a Gauss-Markov random field, we're going to define where the arcs are in order to have a neighborhood. And then we have to estimate parameters which do the strengths of the correlations in the different direction. So down here in the bottom is kind of the key point, which is if I'm in D dimensions, as opposed to 2 here, there are D plus 2 parameters that I have to estimate. And then the fraction of non-zero elements in my matrix Q is about 2D over N. Remember, N is the number of feasible solutions. That's going to be big. D is the dimension. So this matrix is typically going to be very, very, very sparse, which allows us to exploit sparse matrix linear algebra computations to deal with inverses and parts of inverses very efficiently. Now, complete expected improvement, if you haven't seen expected improvement kinds of ideas before, expected improvement fundamentally says, in this Bayesian sense, looking at the posterior distribution, given the data that I've looked at, how much better do I think a solution X might be than what I believe is my current optimal, right? So CEI of X, the complete expected improvement of solution X, is the expected value over the posterior distribution of the maximum of Y of X. Remember that represents the objective function value of solution X, minus X hat, what I currently think is the best solution, the max of that and 0, conditional on the data that I've observed. So what we were able to do was derive, it's a messy formula, but a formula that, that expresses CEI and fully accounts for all of the stochastic nature in the problem, my unknown response surface and my simulation estimation error. Again, it only requires the diagonal element, which is the variance, and one column, which is the covariance, in order to compute the CEI for all solutions. And kind of as a bonus we didn't think about when we started, you can also use CEI as a stopping criterion. So if I'm running my optimization and at some point the expected improvement of every other feasible solution appears to be no more than delta from my current incumbent best, then that's a reasonable way to stop the optimization early. Okay, so I just wanted to show one picture. This again is a two-dimensional problem. It's kind of like that inventory problem. So you've got X1 and X2. It's a small problem, just so I could show you, it's only got 10,000 feasible solutions. And we know what the true objective function surface looks like, and it's non-convex, and it's got a ridge, and it's messy. Now, what you see in this heat map is every place that you see a dot, our algorithm simulated that feasible solution. And when the dots are more black, that means it returned to that solution and simulated it again to get more information, more replications, and a better estimate. And what you can see is that it very quickly learns that there aren't good solutions in this space. The ridge of feasible solutions gets identified pretty quickly, and it's focusing in and spending more simulation effort where the true optimal solution is. And this is what Bayesian optimization does so well. It very quickly learns what good areas of the feasible region are and closes in on them. Now, this is much longer than we would normally expect to run our algorithm on a realistic problem that's really, really expensive. So this was just run longer so you could get a little more sense of how it does the explanation, or how it does the exploration. Okay, so this is the last slide. So I'm fundamentally, as Chris said, trained as a statistician, and my application areas are operational research. But one of the things we've really learned over the last decade is CS, computer science issues, really matter when we want to deal with large numbers of feasible solutions or expensive simulations. And I've sloughed over it in this talk, but there's not one unique parallel architecture, and customization to the specific architecture, as we have well learned, can really, really matter. We've learned that MPI, message passing interface, is a really conceptually easy way to program these things, but you can have really unexpected behavior in MPI type environments, and it does take time to pass and process messages. Shared memory environments are really nice to be able to avoid that. And of course, in a realistic setting, your processors may not be heterogeneous. Results can be lost, right? And, as I said, memory might be shared or not. In our setting, the simulation programs themselves can also often be quite large, and there is overhead to load a simulation program on a processor, and it can sometimes be substantial. So we have to think about the setup time for each simulation we want to do, as well as the per-replication time. I didn't talk anything about assigning pseudo-random numbers, but assigning pseudo-random numbers in parallel to achieve what you want can be very tricky. And then finally here, I have focused on parallelizing the simulations that we do, but the calculations we do, like those sparse matrix inverses we have to compute in the GMRF setting, those calculations can be parallelized as well, and that can also make a lot of difference in how much simulation you can do. And Chris, that's it. I'd be happy to take questions at this point.
Great, thank you very much, Barry. I'll give you a round of applause because don't get the usual round of applause in the virtual world, I'm afraid. Okay, so the questions, we have 2 questions already in the chat, and please, if anyone has any further questions, then add them, and we'll try and get through them as best we can with the time that we have. So I'm not sure if Barry, you can see this as well, but I'll read them out anyway. So the first question is from Shane Lawrence. Does the average estimated solution have to remain the same throughout the process to simulation, or can it be updated as the process progresses?
Yes, and typically in all of our, I'm going to pull up the chat here as well. So in everything that I talked about today, things were updated as we got more data. So absolutely. It's sort of critical in the sequential ranking and selection setting, right? What ranking selection, the whole body of literature is trying to do is to simulate sort of little dollops, little batches of things until I can get rid of things. And then I'm updating the things that I have all the way along. In the GMRF algorithm, we also, when we revisit solutions, we update the information and update the means. And in my field, whether it has any practical relevance or not, it's often important to prove asymptotic convergence, that is in the limit that you would reach the optimal solution. And revisiting solutions tends to be the standard way to make that proof work.
Second question is from Robert Schoen. How can rank and selection methods be adapted to dynamic problems in which the performances of the solutions might change over time? So the best solution at one time might not be best at a different time after some elements of the system change or further information becomes available.
Yeah, so thanks for that question. I almost feel like I staged you to ask that question. So an area in which I am working and a number of other people are working, we're not good at naming things, so you may not like the name, but we call it ranking and selection with covariates. So it is very much the setting in which you are talking about, where I am what the best choice is, say among my K things that I can do, may very well depend on information I don't get until right before I make a decision. And so there is a good bit of research going on in the area of what we call ranking and selection with with covariates. Now, that only partly gets to your question. And so I'm going to make a confession here, which is we are much better in the simulation optimization world at static optimizations than we are at policy optimizations, right? Meaning that what I'm trying to do is come up with a policy, the sort of thing reinforcement learning or something like that would do. So ranking selection with covariates is kind of a policy-oriented thing, but it's not as dynamic.
Thank you. One more question. How are the Gauss Markov random field algorithms compared to Markov chain Monte Carlo methods?
So you may have to help me a little bit with this question. I think of MC methods as a way of being able to evaluate the posterior distribution, as opposed to an optimization method in and of itself. So you may be thinking about something that I'm not aware of. In our particular setting, I mean, I didn't go into any assumptions in anything that I did here, but we're able to actually compute the posterior and compute any measures we need based on the posterior without needing an MC kind of way to do it. Where that might come up for me, at least the way I think about it, is if I had some sort of different discrete random field for which I couldn't necessarily evaluate the posterior distribution directly, and I might need the MC to be able to do that. So I hope that that's related to your question. Please type in something more if not.
I think we have time maybe just for one more question.
Okay.
There isn't one, so I get to ask one, which is great.
Okay.
So at the very beginning, you gave this really cool example of these, I think you call them vertiports, the vertical taxis. Yeah. You would simulate for. So I was wondering, so obviously these don't exist yet, so there's no data. So how do you trust the simulator is going to replicate what's actually happening in the real world? Yeah,
so this is, you know, I made this point about simulation being data analytics for systems that don't exist. So this comes up in anything that we do in simulation. And so a lot of what we're doing in that kind of environment is to try to figure out what results might be sensitive to, as opposed to trying to make predictions about exactly what would happen. Because as we get closer to, I mean, right now, most people, when they think about these, assume battery technology that doesn't exist. Right? They say, we're going to suppose that batteries. So a lot of what we do in that environment is sort of what I call parametric simulation. Let's do a variety of simulations, assuming batteries have this characteristic, right, on up to this characteristic. So really sort of, I don't think optimization is as good an idea in something that's that speculative. But I do think experimental design, in terms of looking over a space of possible levels of capabilities that could be there, even including customer willingness to get in an automated air taxi. That's the kind of thing that simulation can do well, but not as good at predicting exactly what would happen.
Okay. Great, thank you very much. So I think we're coming up to the hour now, so I'll bring the session to a close. So thank you, Barry, once again for an excellent talk, and thank you for those who contributed questions, and for everyone who joined us today. Just a reminder that the next DCE webinar is next month, so please go to the DCE website to find information about that and to register if you're not already registered. You should already be registered for the series, but just in case, please go to the website and register, and I'll see you all next time. Goodbye.
Thank you.